Good morning to all of you. Today we are going to learn the repeated eigenvalue for the case of 3 by 3 system, where we have the first example where even though you have 3 repeated eigenvalue, but in this case will lead to 3 different eigenvectors. For example, solve the y primes 0, 1, 1, 1, 0, 1, 1, 1, 0, y. Okay, if it assumes y, the solution of y is actually e lambda x v, where the lambda and v is an eigenvalue and eigenvector, will lead to the homogeneous system a minus lambda I here, this is a eigenvector, eigenvalue, v is eigenvector, v equal to 0. Okay, and then we have here a minus lambda I, where you put out the matrix A is actually, we have this 0, 1, 1 in vertical forms, 1, 0, 1, so we have 1, 1, 0. Okay, minus lambda is the eigenvalue that we want to find it. Okay, identity matrix, you have 1. If the A is 1 by 1, 3 by 3, then the identity matrix is a 3 by 3 also. This is the A minus lambda I. Okay, multiply with your vector V. That's the vector V as a x, y, z. So equal to 0 vector. Hence, k for A minus lambda I, you will have k. This is 0, 1, 1, 1, 0, 1, 1, 1, 0. Minus lambda times the identity matrix only effects at the diagonal. X, y, z equal to your 0 vector. Hence k, you take now you can subtract element by element. So 0 minus lambda. Okay, is only changes at the main diagonal, because you minus with lambda I, where it's only take change just on the diagonal value. That's why I have 0 minus lambda is minus lambda. Okay, at here A, the matrix A at the diagonal is all 0 value. So 0 minus lambda here at the third diagonal, 0 minus lambda is minus lambda. So this is your A minus lambda, only changes at the main diagonal. Takes the A value here at the main diagonal, deduct with the lambda minus lambda at the diagonal. So your upper diagonal, lower diagonal, there's no changes. So this is if you assume the solution for that homogeneous system, the homogeneous system, if you assume the homogeneous system, y prime equal to your ay, y prime equal to ay. Okay, this is the a. Then you have the y prime equal to ay. The solution, if you assume the y is actually you have e lambda x times the vector v, will lead to the homogeneous system A minus lambda I equal to 0. Yeah. And then to find the eigenvalue, we have to let the determinant of this A minus lambda I equal to 0. So that's why to get the eigenvalue, we'll let the determinant of A minus lambda I equal to 0. Hence, just now it's a round bracket. determinant is a straight line, so this stands for determinants. Okay, I hope you remember how to find the determinant of the, okay, for the 3 by 3 matrix. You can take, okay, any row or column. Normally we'll take a row or column which consists of, okay, more 0, but in this case any row or any column almost the same, because we have, okay, we don't have a 0 entries there. Okay, let's say I take, okay, first row. Okay, I will pivot at the first row. Okay, and then remember we have the signs. Okay, it's actually start from positive, okay, alternate. Then you may take, okay, pivot at any column or any row. Okay, now I'm going to take the first row here. So the sign is actually positive, negative, positive. Then I'm taking the first one. I pivot at the first row, so I got negative lambda, positive times negative lambda. Okay, if you take the first row, then you just cross. So we'll, okay, left or 2 by 2, okay, determinant of 2 by 2. So you got here negative lambda, this is 1, this is 1, this is negative lambda. Okay, second, okay, value here multiplied by negative. So you got negative. Okay, and then here. Okay, now I'm taking the second one, first row, second column. So you cross it. So remember the second value here, this is negative. So you left 1, 1, 1, negative lambda. So minus, this is 1, 1, 1, negative lambda. Okay, and then the third value, this is positive, so plus 1. I'm going to take like this, right here. So the third, okay, this is negative 1, this is multiplied by negative 1, this is multiplied by positive 1. So left, okay, this 2 by 2 matrix, determinant, sorry, 1, 1. So negative lambda, 1, and equal to 0. Then you, okay, just do 3 times determinant of 3 by 3, 3 times determinant of 2 by 2. So hope you remember how you find determinant. The main diagonal minus with, okay, the other diagonal. So you have here negative lambda. So you have negative lambda times negative lambda will be lambda squared. So minus 1 here. Okay, so negative. Then this one is, okay, 1 times negative lambda. So you got negative lambda. So this is minus 1. So plus, you have 1 times 1 is 1. So minus with negative lambda, so become 1 plus lambda equal to 0. Okay, expand and simplify, you will get a characteristic of equation. Solving a characteristic equation, you should have 3 eigenvalues. Because you got here negative lambda times lambda squared. So you got negative lambda cubed. So negative lambda times negative 1, so it's plus lambda. So expand the negative in. So this one is plus lambda. So this is plus 1. And then plus 1 plus lambda equal to 0. So, okay, simplify it against negative lambda plus 3 lambda plus 2 equal to 0. Okay, and change the sign by multiply both hand side by negative. So I get, okay, lambda squared minus 3 lambda minus 2 equal to 0. Okay, you may solve it using your scientific calculator. Equation modes. Okay, you solving the polynomial, so number 2 of degree 3. Key in the coefficient of a polynomial equation. Be careful, you don't have quadratic terms. So cubic term, the coefficient is 1. Okay, x squared term is 0. Okay, linear term is negative 3. Constant term is negative 2. So you get, okay, 2, negative 1. Okay, you have only get 2 roots. So mean one of it is actually repeated. Okay, from calculator you obtain actually 2 and 1. So means you have the root 2 and 1. Sorry, 2 and 1 or 2 negative? 2 and negative 1. Means you give from the calculator here, you obtain your lambda is negative 1, lambda 2 is 2. So must have one of it. Okay, you have here negative 1, 2. So cubic we should have 3 roots, however you obtain only 2 roots. So here you have to guess back, okay, which one is a repeated, okay, repeated eigenvalue. So we have lambda plus 1. So root is negative 1, so means your factor is lambda plus 1. This one the root is, okay, 2, so means your factor is lambda minus 2. So you should guess this one is what value, so that you will get a constant here, because lambda times lambda, lambda you got lambda cube. So you should guess, okay, this one, is it plus 1? Is it plus 1 or minus 2? Okay, let's say I guess it is plus 1, hence you just multiply the constant part 1 times negative 2 times 1, you get back negative 2. So the repeated k value is actually lambda k equal to negative 1. Because if you put k here, if you put, let's say, is, if you guess the repeated is negative 2, mean the repeated is lambda equal to 2, then this will be minus 2. So minus 2 times minus 2, 4 times 1 is 4, which is wrong. That's why repeated eigenvalue is actually lambda equal to negative 1. So mean we have actually lambda 1 is actually lambda 1 equal to negative 1. Okay. Also equal to lambda 2, and then lambda 3 is negative 1. So this case is actually not 3 repeated eigenvalue we got. Okay, system A is 2 by 2, 3 by 3, but each to 2 same eigenvalue, 1 different eigenvalue, and we get actually in this case we have 3 different eigenvectors. So after we get the eigenvalue, okay, after we get the eigenvalue, okay, we are going to find eigenvector. Okay, to find eigenvector, the first eigenvector, we have a lambda 1, and we take a lambda 3 in this case is 2. 3 is actually 2. Okay, and we let the smaller eigenvalue is a smaller value, so we have a lambda 1 equal to lambda 2 equal to negative 1. Then we are going to find V1 from the homogeneous system A minus lambda I V1 equal to 0. Okay, so this is A minus lambda I V1 equal to this is A minus lambda I V equal to 0. So you plug in here lambda 1 equal to negative 1 into the, okay, this one is actually A minus lambda I. A minus lambda I V equal to 0. So plug in lambda here by negative 1. So you plug in -1 to negative lambda, so all the main diagonal are become 1. So cell A minus lambda 1 IV, or after you plug in all the lambda 1 equal lambda 2 equal -1, okay, hence you get each cell is actually 1. And this one is actually, when you see, all the cell are actually 1. Zero vector. Hence, 3 unknown we reduce to only one equation, which is x plus y plus z equal to 0. So x plus y plus z equal to 0. If we let x equal to s, cause 3 unknown with 1 equations, okay, we have infinite many solutions. That's why if we let x equal to s, y equal to t, then z will be equal to -s minus t. Right? This is s, this is t. Hence, you get the z is actually z is minus s minus t. So x is s, y is t, z is -s, -t. So break into two vector which consists of parameter s and parameter t. So x is only 1s, 0t, don't have t. Y is 0s plus 1t. Okay, z is -1s plus -1t. Hence we have 2. If we let s equal to 1, t equal to 1, mean let the s equal to 1, t equal to 1. So this will be your v1, this will be v2. Hence, for two same eigenvalue, we obtain actually two eigenvector already. 1, 0, -1, 0, 1, -1. Yeah. This is a v1, this will be v2. We have two eigenvector already. Okay, the third step, by plug in the lambda 3 equal to 2. Plug in the lambda 3, just now they obtained from the calculator. Okay, you have 3 eigenvalue, 2 are same. 2 are same, which is lambda 1 equal to lambda 2 equal to -1, lambda 3 equal to 2. So plug in lambda 3 equal to 2 into the homogeneous system. Okay, this is A minus lambda I, this part, this is V equal to 0. Plug in now, so lambda 3 equal to 2. Okay, so you get this one. Because initially A here is 0, so minus with your eigenvalue which is 2, so minus 2. Okay, now it is not easy to see whether these 3 rows can be reduced to only 1 row. That's why we need to use suitable row operation. Try to eliminate it to the upper diagonal matrix. So not like just now, 3 equations, you can easily see it is actually reduced to only 1 equation. Just now, after you plug in lambda 1 equal lambda 2 equal to -1, you can see that 3 rows actually reduced to the same row, which is x plus y plus z equal to 0. But in this case, it's not easy to see. After you plug in lambda 3 equal to equal to 2, so we get here this system, and it's not easy to see whether they are actually equivalent. We can be reduced to only 1 row or 2 rows. That's why we need some row operation. Okay, my row operations here, I'm going to actually reduce these 2 cells, become 0. By using my row operation, is actually, I see this is -2. So if second row, I times 2. Mean if second row, if I multiply by 2, and like this, if I times 2 to second row, my intention is actually makes this cell become 0. So there's no changes on row 1. I just keep like this. if my second row I times 2, so this one times 2, negative 4, this one times 2. Then if I add up row 1 and 2 times row 2, I put into row 2. I put into row 2. So there's no changes on the row 1. Okay. So now you add up these two rows. Negative 2 plus 2, 0. Okay, 1 plus negative 4. 1 plus negative 4. So you have negative 3. 1 plus 2, you have 3. So we have successfully reduced A to 1. Second row, first column become 0. Okay, now I'm going to reduce, or eliminate cell A31 become 0. Okay, see this negative 2. So here if I multiply by 2, okay, and I also take 2 times of row 3, put it 2 here. In the initial row 3, I times 2. So I got 2, 2, negative 2. So now if I add up, row 1 and if I add up, this one is actually row 1. Row 1 with 2 times of row 3 here. Row 1 with 2 times row 3. So negative 2 plus 2, 0. So 1 plus 2, you have 3. 1 plus negative 2. 1 plus negative 2. This one I think I forgot to times 2. Negative 2 times 2, this is negative 4. So 1 plus negative 4 minus 3. So this is what you got, okay? And now you see, focus on the latest system here. Do you notice if row 3 and row 2 are actually equivalent? If the row 3 here, row 3 you multiply by negative 1, actually you get back to negative 2, this is 0, this is 0, this 1, this negative 3, this 1, this is 3. Negative third row, you will multiply by negative, so negative 3, 3. So x, y, z equal to 0. Hence, these two rows are actually same, so you can reduce it. So that's why, from 3 unknown with 3 equations, we reduce to only 2 equations only. Because these two are same. These two are same. So you reduce it to only negative 2. If they are same, it will add up. Negative 1, 1, 1. This is actually 0. Negative 3, 3. This one becomes 0, 0, 0. X, y, z equal to 0. If they are same. Or actually from here, you take row 2 add up with row 3. Negative 3 plus 3. Then put into your row 3. Negative 3 plus 3. That's why you get actually 0. 3 add up with negative 3, you got 0. This is using row operation, or row 3 times negative 1, we see they are actually equivalent. That's why this one can be cancelled. That's why from 3 unknown with 3 equations, we reduce to only 2 equations only. 2 equations only. And then from here, we can read back, the system is actually equation 1. Here, we have negative 2x plus y plus z equal to 0. From second row here, we have negative 3x. Sorry, this is y. We have from here, negative 2x plus y plus z equal to 0. From second equations here, negative 3y plus 3z equal to 0. Yeah. And then, from the second equation here, actually you have 3y equal to 3z. Mean y equal to z. So if y is s, then z will be s. Okay. Then you plug in y is s, z is s. So you have negative 2x plus 2s equal to 0. Or from here, you have got 2x equal to 2s. So x equal to s. So we obtain the third eigenvector where each element value is 1s. By taking s equal to 1, you get your v3 is actually 1, 1, 1. Hence, okay, the general solution, because we have, even though we got two same eigenvector but each to v1, v2, then this is v3. So your solution is actually, you have, this is a, this is v1, so exponent, okay, lambda 1 t, plus this is b, this is v2 exponent, okay, lambda 1 equal to lambda 2 in this case, either t or x, c, this is v3 exponent lambda, okay, 3 t. Because the y may be dependent variable is t or x, so look at the equation properly back. So here, this is a v1, this is a v2, this is a v3. Okay, lambda 1 equal to lambda 2 equal to negative 1, lambda 3 equal to 2. So this is a 3 by 3 system where we have the two repeated eigenvalue, but each 3 different eigenvector. Then 2 repeated eigenvalue, but have 3 different eigenvector. So this is a case where we have a system 3 by 3, but we get two repeated eigenvalue, which leads to, this case is actually, even though two repeated eigenvalue, lambda 1 equal to lambda 2 equal to negative 1, but we get v1, v2. Okay, and then another eigenvalue, lambda 2 equal to 2, we get v3. Hence the solution y is actually a v1 exponent lambda 1 t plus b v2 exponent lambda 2 t plus c v3 exponent lambda 3 t. Okay, look like 3 different eigenvalue, 3 different eigenvalue and eigenvector, but actually lambda 1 equal to lambda 2 in this case. So I conclude back to find the solution of the homogeneous system. First of all, you will find, you assume our y is actually v exponent lambda, x or t depend on the question whether the y is dependent on x or dependent on t. So by assuming y equal to e lambda x or t v will lead to the homogeneous system a minus lambda I v equal to 0. Okay, after obtaining the eigenvalue, eigenvector, then you can get back the solution. To get the eigenvalue, we'll let the determinant of your a minus lambda I equal to 0. And then you solve your determinants, 3 by 3. You can actually take any row or any column, but be careful of the sign. And normally we will take the row or column which consists 0, because 0 times anything you get 0, but in this case you can take any row or any column, but in this case I take first row. If you take first row, so mean you must have negative, positive times negative lambda. This is negative times 1, this is positive times 1. Then how I get this one? For first row, first column, you cross it, you get this one. For second second cell, this is negative times 1, you cross here. You cross this, you get this. For third one, this positive one, so you cross this here, so you get here. Then you do determinant of 2 by 2, which is the main diagonal, subtract with the other diagonal. Okay, expand, simplify carefully, and you can use your scientific calculator, okay, to obtain it. Okay, in this case, just key in the coefficient for your cubic equation, where a in this case is 1, b we don't have a quadratic term, 0. Okay, linear term c is -3, d is actually -2. Key into your calculator, you obtain only 2 and -1. You obtain 2 and -1. So which is the repeated eigenvalue? If you have the roots, okay, -1, the factor will be lambda plus 1. Root is 2, so the factor which will be lambda minus 2. So you put it lambda plus 1 times lambda minus 2. So you have to guess the third repeated, is it -1 or 2? So must be tallied back with the constant here. So if we put is root is -1, so lambda plus 1. So 1 times -2 times 1, you get -2. So the repeated is lambda equal to -1. Then you plug in, okay, lambda 1 equal to lambda 2 equal to -1 into the homogeneous system A minus lambda IV equal to 0. Okay, solve it, you will get, okay, for this case we get actually like this. So 3 unknown with 3 equations, however reduced to only 1 equation, which is only x plus y plus z equal to 0. That's why if x here is s, y is s, then y will be t, then z will be -s, -t. So let s equal to 1, t equal to 1, you get 2 eigenvector. Then similarly plug in, okay, lambda 3 equal to 2 into the homogeneous system A minus lambda I, solving for your, okay, V3, we get a new, okay, eigenvector V3. So lastly, the solution will be A V1 exponent lambda 1 t plus B V2 exponent lambda 2 t plus C V3 exponent lambda 3 t. Okay, with this, okay, thank you for your attention.